with us, Anne-Mieke?
Yeah, I'm there.
Can everyone hear me?
So, hello everyone. Do you hear me? Yeah, okay.
Yeah, everyone can hear you.
I will turn the screen so that you can see the crowd, Anne-Mieke. Or do you want to see
Yeah,
the...
it's okay.
That
I
way
see.
she can see the
Oh, yeah,
presentation.
you want to see the... Okay, sorry.
Yeah, it's okay. Yeah. So, hi from Lisbon. I'm sorry I'm not there tonight. I hope it goes well. I will talk relatively slowly because I know if I talk too fast, Skype tends to block. So if there's an overload of sound, Skype tends to block. I heard the talks so far, and I can already predict that the first country that will be affected by dengue in Europe will be Portugal. Because dengue last year has been transmitting locally on one of the islands in Madeira. And so we are investigating dengue, and together with some people here in Portugal, I'm going to Brazil in December for a Zika project, and we're also involved in a dengue project there. But the slides that I'm going to show are not about dengue. I didn't have anything prepared for dengue. I prepared these slides for the Luciad workshop last week, and I'm giving you, so together with Daniel, we prepared 3 demos, and I'm giving you one of these demos. I'm first going to give you some background information of what kind of data are we looking at. So I'm going to start with the first slide, well, slide number 2 actually, about phylogenetic trees and evolution. On the left there, you see a phylogenetic tree, and on the right, you see on the top what people sometimes think is evolution, which is not the case. At the bottom, you see that evolution is descendants from a common ancestor. So the tree on the left gives the evolution of species, but what you actually have to imagine is that all the species are alive today, and what you reconstruct with a phylogenetic tree is the history of the past. So now we go to the next slide. The kind of data that we use to reconstruct phylogenetic trees are shown there, are listed on the left, but the data that we are using in this particular case to construct phylogenetic trees for infectious diseases, the case that I'm going to show is about Ebola virus, which you heard about in the previous talk. And we are using nucleotide sequences. That's one of the data sources that you can use to build phylogenetic trees. And on the right there, you see a phylogenetic tree. And I indicated a time axis on that phylogenetic tree. So the tree there grows from left to right. Left is the past and right is the present. We go to the next slide. So the phylogenetic tree gives the information, the historical information, the evolution of the virus genetic sequences. Now, the virus genetic sequences can be annotated with other data. For example, geographic location. Now, the next slide gives you such a phylogenetic tree where there is annotation on the tree, on the viruses. So the viruses that were used to build the tree are the dots. The green dots, viruses sampled in location A, and the blue dots, viruses sampled in location B. With a phylogenetic tree, we see the history of these viruses. So we can reconstruct the ancestral location of the ancestral virus. And that you can see in the next slide. So this reconstruction can be done with several methods, but you can imagine that what you see there is a most parsimonious reconstruction of the ancestral state of that virus. Sorry. Now, if we have the ancestral state, then we can start counting migration events in the next slide. So if you have in the part of the tree where everything is location A, you suddenly see popping up another color, location B, you can deduce from this that there was a migration from A to B. And here you see 4 counts of migration. So you see 4 times a jump from green to blue. That's 4 migration events. Now, if we have in the next slide, if we have additional metadata on these viral sequences, if we have additional metadata about time, then we can do even more. Now, the next slide is just a depiction of how we map time on a phylogenetic tree. So imagine that you are going to the desert and you see a cactus there, and you measure the branches of the cactus, and 10 years later you come back. You measure again the length of the branches of this cactus. So then you see some branches have been growing 80 centimeters per decade, another 65, another 50 centimeters per decade. You basically have a time frame on this cactus and you have a growth rate. And in the next slide, you can see that we use this growth rate, which is the evolutionary rate of the virus, to reconstruct the timing of ancestral nodes in this virus. So then the next slide shows what else you can do with a phylogenetic tree. If we go to the next slide, you can see that in a phylogenetic tree, that in this particular slide grows from left to right, so the past is left, the present is right. If you go in time, so we built this time based on the method that I showed, measuring evolution over time. You reconstruct the ancestral states of the time of the ancestral nodes. And if you go through time, you can actually count, Daniel, maybe you can show in the slide, you can actually count the number of branches that are in one particular point in time. And if you move from left to right, you can see that you have splits, which is a new infection that happens. And you can see how many splits you have in a particular time frame. So on the bottom of that slide, you see if the splits over time are constant, are growing constant, then you have a linear increase in your epidemic. You can see this is an exponential axis. But if suddenly you have a lot more splits, you have a lot more branches created, then you have an exponential increase in your epidemic. So you can actually reconstruct the population size and changes in population size of an epidemic from a phylogenetic tree. Now let's go to the next slide. Let's take an example, Ebola. Ebola is a zoonotic virus. We think that bats are the original host, so the host species in which Ebola continues to live in the environment, and that occasional spillovers from the natural host to new hosts cause disease in the new host. And we know that Ebola causes diseases in non-human primates, in gorilla that you see there, in chimpanzees, and also in humans. And then Ebola can be transmitted, as was said by the previous speaker, when you touch other people. Ebola can spread through funeral practices, unprotected healthcare workers, unprotected contact with blood and body fluids. In the next slide, you see some of the symptoms of Ebola. I don't want to scare you too much, so we go on to the next slide. And the recent Western African outbreak that was talked about by the previous speaker has stopped. So it started in 2014, and in 2016, the last 2 boys were discharged from an Ebola treatment center. A lot of people died, but a lot of people also survived. Now, using the kind of method that I explained, the phylogenetic trees, we can try to reconstruct what happened with Ebola. So if you now go to the next slide, here is the actual counts of Ebola infection through serology over the months during the outbreak. And traditionally, we've used these maps with prevalence of Ebola per county, and you see a color code in the bottom right, and so the more red, the higher the incidence and prevalence of Ebola. Now, in the next slide, you see a phylogenetic tree of a huge number of virus genetic sequences. And the phylogenetic tree has been colored according to the reconstructed ancestral location. So we know the location of all the strains, which are the end dots on this tree. Then the reconstructed ancestral node has been annotated with the most likely place where this ancestral node existed. So the tree has been colored according to geographic area. You also see in the bottom is a time axis. From the information of what we call time-stamped virus sequences, we can build a molecular clock and reconstruct when these ancestral nodes existed. So when this virus existed in these particular geographic locations. And you can see that the outbreak, the first cases were in 2014. So you can see that the outbreak develops from 2014 until in this slide up to 2015, but we know that it extended up to 2016. So from this phylogenetic tree, we then try to reconstruct how the virus moved. And this here shows you how we illustrate this in publications. So we have a map, we have arrows that we draw, which we reconstruct these arrows from the phylogenetic tree. So that was when I contacted Lucia to see if we can do it in a nicer way. And now Daniel is going to give you a small demo of the Ebola epidemic.
Can I take that? Okay, so hello everyone. My name is Daniel, as Anne-Mieke has already kindly introduced me. We did a cooperation with Anne-Mieke and the Rega Institute for Medical Sciences a while ago, and we had a look at 3 use cases, and I'm about to show you a demo for one of those use cases. So this here is a data set that we got from Anne-Mieke, where we show the evolution of the Ebola virus over time. And over here we have a time axis over here we have a visual representation of space and time, so geospatial information. So one of the things that we can do here is I can just play this, and it's a very sensitive mouse. So what you see here is an animation of the outbreak as it's happening. The origin is here in Guinea, and then it spreads all the way across. On the timeline here, what you see is the infectious burden, which means the estimation of how much infection counts, how much the outbreak is in a specific country. So we have Sierra Leone in red, Liberia in green, and Guinea in purple. And it matches the same data as on the map. What you actually see when you go on the timeline from left to right is jumps from one region to another region. And really, this is a visual representation on the map of the phylogenetic tree. Each of the jumps is a branch in the tree where the parent and the child node are not on the same location. That's how you get a jump, and that's how we track the virus as it spreads over time. So when we have a look at this data set, we can do a bit more things. We can do a bit of analysis. One of the things is that the phylogenetic tree is annotated with metadata. For instance, in this case, there's an aspect of time. There's also an aspect of location. So we could add, for instance, a filter on the origin to Huequedou, and we could make, for instance, that yellow. So then when we have a look at the origin, right here in Huequedou, and we just play our little animation, we can see as the outbreak is occurring and it slowly starts spreading across to other countries. And now we see a big explosion of outbreaks basically happening right here in Kailahun. So how does that happen? Well, if we correlate this data to a population density, we can clearly see that as soon as the virus reaches a state of high population, in this case, darker areas or highly populated districts, we see that we have two peaks in the data set where a big outbreak occurs. One is over here in Kailahun, which is a very densely populated area. And then later, we have a second peak as we reach the western rural areas, which are also very highly populated areas. So you can really see the explosion happening. In fact, let me just add an additional filter on Kailahun. If we make this red, for instance, we can really see the impact of what happens when Ebola reached a highly dense populated area. It starts spreading all around and it just explodes. So as Anne-Mieke already mentioned, we have two other demos that I'm not going to get into, but if you want to see them, please have a talk with me after the presentation. I would like to show them to you.
Excuse me?
Yes?
The curve that we see here is actually someone driving by car or public transportation, or how do you modelize? What does this mean, the curve?
Yeah, so when we looked at this right now, what you're referring to is this curve, right? The fact that it curves.
Yeah.
It doesn't really have a meaning because the jumps from one location to another location, you could say that they're geodetic, but really what's happening is you're just modeling a start and an end location. We didn't really want to associate it with roads right now. But a possibility would exist to associate this data, for instance, with roads or other modes of transportation by following highways. This would be an option. We haven't gotten that far yet in the integration, but it would be a nice option. Yes?
Yeah. Sorry, I was in Sierra Leone doing Ebola. So one of the things that is interesting is when you put it all together is when you go from Gedek, when you look at the Kisi, where the Kisis live, where they move, where they go when they look for protection, when they look for care, when they look for a family to take care of them. You follow the road, you follow the Kisi areas. It's when the Kisi group gets to the highly populated areas that then it's kind of a not controlled transmission, because then people from different ethnic groups live together. And then they spread where they have their friends, where they have their families, etc. Then you look at, and when you started with the one in Gedeko, you can really see the transmission from where the cases are. They go to their nucleus centers, they go to the areas where they confluence, and then they go to another. There are two areas that are important. One is in Kisi City in Freetown, and the other one is in Gambia and the area of Porloco, which are Kisi areas as well. And then the transmission around there is also the issue of the other Kisi area. Important is the area of the border with Guinea and Gambia, which is Forecaria. They started to cruise the borders and they started to infect each other, and that was what's going on in there. So when you start looking into those things and you start looking at the population and understanding their needs, etc., that's when you can control the outbreak. So the issues that we did to control the outbreak is understand the population, understand their dynamics, understand their needs, understand their culture, and be able to approach them. Because of the things that you have to, and it's so interesting, and that's why I'm so glad that we are all together, because then you look at the history, then you look at the sociology, then you look at the anthropology, then you look at the socioeconomics. Why is that they didn't trust the government? Because those are the areas that used to be harvest for a slave trade. They have always been displaced, they have always been used by the government. So they don't trust the government. The government in Sierra Leone is Creole. So it comes from the Freetown, the free slaves that the UK settled there at the age of 1800s, because they were the survivors, so they fought with the UK, with the British, with the Imperial Army, the independence of the United States. Then they moved them to London. They were living in poverty. They created Freetown, and that's how they became the powerful group in there, the Creoles. But the Temnes were living there before, so you have to understand all of those interactions. And when you start understanding those interactions, it's when you can start controlling the outbreak. Simple?
So,
not simple, but complicated, lots of deaths, sorry.
So as that example, could you look at how another disease, completely unrelated but serious, moves around and maybe see if it follows the same patterns because they go to the families or go to the same sources of health?
Yeah, it depends on what is the rate of infection and the mode of infection and transmission. So with dengue, back again, you need a human being. The other thing that is important is that you have to understand that the fruit bat is a delicacy, or was a delicacy, and they were eating fruit bats every day, or whenever they could harvest them or control or hunt them. So, but that depends on where you go. But back again, if you look at influenza, I mean, you know that the place where influenza can usually emerge, with the exception of one of the things that we discovered in influenza, because I was sitting in my desk one day and looking at what to do, and I started to see, there's something going on in Mexico, what is going on? But there we started to understand that the animal interface that we were looking before was so important, and those pigs were coming from California, where we have already some mixing in terms of the H3N2, the H1N1, and we didn't detect that because we weren't doing animal surveillance. And then they mixed with the human beings in Mexico, in those areas, and that's where H1N1 started. And when we started to look at the phylogenetics, etc., and the transmission, we understood that that was going to be a bad influenza season, but not a pandemic. We transferred that information to WHO, but didn't listen. So it became the whole thing. So, but that is the part that is so interesting, putting people together and start thinking, what else? Why? What do you see? And go to the field and observe what you are thinking. It matches or not with what you see in the field.
Anne-Mieke, you still have some slides left? I'll give the word back to you.
No, the next slides are just advertisement and acknowledgement. So we have a book, a handbook that we use for phylogenetic analysis. So we teach these kind of analysis every year in a course, but that's not for this public. And this is more for the biology background, the virologist public.
Excellent. Well, thank you very much, Anne-Mieke.
Thank you very much.